I guess everyone is sleeping right now, or you're probably falling asleep. I realize I'm the only thing keeping you awake, and that's a hard task because I'm falling asleep as well. But anyway, so now I'm gonna talk about system integration and the OpenStack. What I consider that it's something that OpenStack has done quite well um, in the way it integrates all the services that you need to have running in order to use OpenStack. Necessarily perfect, and there are definitely many issues that we still have to fix. But anyway, at least I think that the way it's being done right now is fairly good. But the thing is that what I'm going to do is I'm gonna walk you through what system integration actually is and the different methods you have to integrate systems. And then I'm going to talk a little bit about a library that we use in OpenStack and that was created by and for OpenStack, although you can use it outside as well for your own projects. But the points where I would like to focus a little bit more on are related to the API and the way you would structure and the way you will integrate your services following a use case similar to OpenStack. So this is me. That's my Twitter handler, and pretty much I'm Flavio, so I'm pretty much everywhere. So if you're interested to look something about me, go there. I work for Red Hat, full stream OpenStack developer, full upstream OpenStack developer. See, I'm falling asleep. This is gonna be fun. I'm part of the RDO team. RDO, if you don't know what RDO means, is a community, an open community of people that make sure that all OpenStack works perfectly in every single role-based distribution out there. So Fedora, CentOS, and all the other distros that are out there. A few other things about me. I'm not going to walk through all of them, but the one that I do always mention is I'm part of the OPW program. It's an outreach program for women, and I'm a mentor of that program. And the reason I'm mentioning this is because OPW is not just for OpenStack, but many other projects as well. So if you are into mentoring people and sharing your knowledge and helping other newcomers into the open source world, I would highly recommend you to sign up there and help out. So what does integrating a system mean? System integration is actually, I mean, the definition behind system integration is actually very simple. It's about getting different subsystems to talk to each other in a kind of standard protocol within your own system, right? So you work on these methods and you work on a protocol and different technologies that you would use to integrate all those subsystems, and you will stick to it, and you will make that your standard in your whole infrastructure. But system integration is actually very simple. It's all just about taking different systems and making them talk to each other and consuming their APIs or whatever they provide from other systems as well. There are different deployments, there are different ways that you can integrate systems. These are probably the most common ones, are the three ones listed here. And the first one is vertical integration, and then you have also star integration and horizontal integration. Let's walk a little bit on those. So vertical integration, it's pretty simple. You have three services. Service A knows how to talk to service B, and service B knows how to talk to service C. It's vertical, like just one service talks to the other one, and the other one talks to the other one. And service A just knows what service B can do for it, but it doesn't know that service B is actually talking to service C as well. Then you have the star integration. Star integration, or also spaghetti integration, like some people call it, it basically means that all the services know what other services do, and you have a service A, service B, and service C talking to each other whenever they need it. So if service B provides something that can be consumed from a service A and service C, they will both talk to service B whenever they need that and whenever they need to call something from them. And there's horizontal integration, which is basically like the star integration, with the only difference that all the services talk to a common service bus, messaging bus. So they do that by sending messages to this horizontal layer, and the other services will get messages out of it and will do something. It doesn't mean that all the services know what other services do. They will know just what the services they're interested into do. right? So if service A needs something from the service B, it will send a message to this communication bus, and service B will eventually get it, do something, and reply back to service A if service A is waiting for a reply. And this is the one that we use the most in OpenStack. It doesn't mean that you cannot mix them somehow. You're free to mix them if you need to. So I wouldn't recommend it. I would probably just stick to whatever method that works best for you, or whatever the architecture works best for you. And I would stick with just one. But we use horizontal integration in OpenStack. We do that because it's easier. It's easier for us, and we do that because it's an easier way to standardize the whole thing, and we can make it a non-opinionated integration method. And it scales very well because you can keep adding more nodes that will talk to that communication bus whenever you need them, and you can scale that horizontally very easily. Instead, if you have a star integration, you will be adding more nodes, but you also have to tell the other nodes in your infrastructure that there are more nodes that they can talk to if they need something from them. So there are different ways to do horizontal integration, and I'm gonna now walk you a little bit through probably some history or not. But there are many different ways to do horizontal integration. Some people know exactly when they are doing it, but when some people use some methods, they might not know that they are actually integrating systems. One of the oldest methods to integrate system is using files. And I mean, files, it works very well for certain cases. I wouldn't recommend it for a production environment with a big system, but they work very well if you have embedded systems. You don't have many resources to run other services in them, in those devices. So you probably will have like 2 small applications that will communicate through a file. So service A will write a message or something to that file, and service B will read it. There are many issues related to files, so like I said, I don't recommend using it. We used to use files to have some kind of distributed locking system in OpenStack that went really bad. So we basically deprecated all that code, and we are now working on something that is also based on horizontal integration and that communicates through the bus. The other way to integrate system horizontally is using databases. So here's the fun thing about databases. It's very common nowadays to have a database deployed in your system, and you have services talking using the same database instance and using the same database resources to store and get data out of it, right? But when you're storing data in a database, you're probably just thinking about you are talking to a service that is holding your data. But when you have 2 different services that are reading and writing to the same database instance, and they are communicating with each other by just storing data there and getting it out of there, you're actually integrating those 2 systems using a database. The way we used databases for integrate our systems in OpenStack is when, so how many of you are familiar with OpenStack, by the way? I keep talking about OpenStack, assuming that everyone knows what it is. Okay, so for those of you that are not familiar with OpenStack, OpenStack is a cloud, cloud provider, basically. It started as an infrastructure service provider, but it just became cloud provider as we added more and more services there. So there's, depending on the services might be split in several smaller services. For example, Nova, which is like, I would bet that you guys are familiar with AWS and all the services provided by Amazon, right? So Nova, which is basically EC2 for OpenStack, so it provides virtualization, it provides computing. It is split in services that do specific things. So you would have the Nova Compute node actually running in the server that has a hypervisor where you want to actually provide virtualization. And you then have a Nova API node, which is running in the server that is facing the user. So the service, the server where you have all your services and bound to a public API, so all your users would talk to that. So when a user asks for a new instance, it would talk to the HTTP API provided by Nova API, and then Nova API would would create a message, and it will send it to the communication. and then the Nova Compute node will take that message and it will spawn a virtual machine. I'm simplifying, I'm oversimplifying this, but that's in a higher level, that's how it works. I'm saying all this because Nova API, when Nova API gets the request, it will create a record in the database for the new instance that has been requested, and then it will send a message to the communication bus. And the only thing Nova API sends to the communication bus is, hey, we need to create a new instance, and this is the instance ID. And the Nova Compute will take that message and will create a new instance. But the database, the record in the database is already there. It just has the basic information that Nova API knew already about the instance. And one of the data that it's stored there is the status of the instance, which at the creation time it would be building, I guess. I don't remember. Like it's building. It's basically saying your instance is being built. The request has been sent to the Nova Compute node, and it will be ready soon. And the Nova Compute node will get that record out of the database, and when the instance is ready, it will update the status of that instance. It will say, okay, your instance is running now. And it will start again that message in the database, that record. So in this way, you're integrating two different services that are meant to do two different things using a database, right? Because they're sharing the same resources in the database, they are storing, and they're reading and writing to the same records and the same resources. Then there's this other way to integrate services, which is using messaging. And I'm talking, messaging is meant to be read as messages, as the smallest unit of data traveling through your system. It's not, I'm not talking here about message brokers. I'm not talking here about any other federation, communication, or whatever protocol you want to put in there. I'm talking about the message as the smallest data unit of data traveling in your system. And it is loosely coupled, which is different from a database where you're tightly coupled to the schema you have there, because you have to respect to, well, depending on the database, if you're using a database as schema-based, you'll have to respect the schema, probably, likely. But anyway, it's loosely coupled because you can send messages, and you are expecting the other end to know what to do with those messages. So when service A sends a message, there's kind of a contract between service A and service B. And service B will get that message, and we will know what to do with that message. It's very common to use this for notifications just because of that. If you don't have a contract, well, it's normally happen without a contract, actually. You just send like service, for example, Nova Compute will say like, hey, we just spawned a new instance. It will send a notification and say like, it was spawned at this time and we did it this way and it's running on this node. And if there's a service interested in consuming those notifications, they will just listen to that specific topic. We'll get those messages and we'll do something with those notifications. So messaging is very common, and it's the base of the next method that I'm going to talk about. It's great because it's loosely coupled, but there are many drawbacks from a loosely coupled integration method because there's no a real contract between the different nodes. And then there's RPC. RPC stands for Remote Procedure. It's not actually a protocol. It's pretty much like a description of how you can integrate systems. It has a contract. When you use RPC, you have a contract with other services that you're talking to, because remote procedure calls are based on exposing through some API some of the features of each service, and the service willing to consume those features, those methods, it will send a message structured in a certain way that the service B can consume and reply back in a way that A can also consume and can process. It is tightly coupled because you have a protocol, you have a wire protocol, you have a contract to respect between both services, but it's still based on messages. So you would create a message, you will send it through whatever bus or communication method you want, and the other service will get the message and will do something with it. And it's probably, well, it's not probably, it's actually the most used way method in right now. So the OpenStack case, so now that I've walked you all through those methods, So in OpenStack is based on the shared nothing architecture, which basically means that each service in OpenStack runs in the most isolated way possible for that service to run. So they don't share any resources, they don't share memory, they don't share processors or anything. They may run in the server, and they may run in the same server, although it's not recommended for all the nodes or the services that need to be executed. But they're isolated in the most, they're isolated, completely isolated, as much as possible. So we use database for inter-service communication. We use RPC for inter-service communication. So like I said, Nova API will send an RPC request to Nova Compute, and Nova Compute will process it. And we use messaging for notifications. So each service, every time one of the services does something, it will send a notification without expecting anyone to process it. It will just say like, hey, we did this. And if someone is interested, they will consume that notification. A good example for this is Ceilometer. Ceilometer is the metering service in OpenStack. So you probably would use, which is actually renamed to telemetry. Anyway, you use that service to gather metrics in your system and know how it is doing, how many virtual machines are running, and when they were running, how many resources are free or are being used. And you can actually build on top of that, right? So you have services that are interested in these notifications just to create data or structure the data in a way that can be analyzed as well. So to do all this, we created this Oslo messaging library that has been improved over time, and it started quite bad because it started very tied to what AMQP is. Do you guys know what AMQP is? Raise your hand. Who knows what AMQP is? Okay. So AMQP is an advanced messaging protocol and for queuing systems, and there was no standard until the 1.0. So RabbitMQ is not using 1.0, so it's not running any AMQP standard. None of the brokers out there are running it right now. 1.0, the version 1.0 of the protocol is a standard, so every broker implementing a specific version of the protocol needs to respect the protocol as it has been stated and written down. And I'm saying all this because the first version of the library started very tied to the previous versions of the protocol and to what the broker could do for us. And then we started adding more brokers, and different things between those brokers came up, and we had to kind of rearrange the whole API and started improving things to support other technologies that are not necessarily broker-based, like ZeroMQ or even AMQP 1.0, which doesn't require a broker to be run. Oslo messaging has support for asynchronous calls and synchronous calls, so you can basically send a message, an RPC request, and wait for a reply back. That would be a synchronous call, obviously. Or you can send an asynchronous call when you want some node to do something and you don't care how much it is going to take or whether it succeeds or not, because you have you have implemented in a way that you don't need a reply back from the system. It has different executors. Are those are the ones that actually execute the task. So when service B in this case gets a task out of the message queue, it will process that task in one of these executors. You have blocking executors, which means that it just blocks for every time it runs, or you have ones based in eventlet, and we're working on the ones based in async.io. It handles connection pools for you, which is something that I would highly recommend when you're talking to a message broker. You have to have some kind of connection pooling. So Oslo messaging does that for you for free. It has drivers for RabbitMQ, QPD, ZeroMQ, and we recently added a protocol-based one, which is based on purely AMQP 1.0, which, just like a ZeroMQ, and I already said, this is brokerless. Talking about message patterns, with Oslo messages, you can easily have producers and consumers. You can easily have publish and subscribe, and you can easily have notifications. I'm not separating notifications here from publish and subscribe. You might say, but you can send notifications in pub/sub way because you just send messages. And if there are subscribers, they will get the messages out of it. And the reason I'm separating these is because in the library they are separated. we wanted to make this difference between what are your notifications, what are the things you're notifying to other services, and what are the things that you are actually sending to services that you care about and that you want them to do something with it. So now that I've said all this, I'm going to talk a little bit about what you need to do, what I would recommend you to do when you want to integrate services in terms of API and in terms of how you would structure them. And I'm saying this because when it comes to system integration, it is very common to start with something very basic and say, I have this, I don't know, I'll just install routing queue, and I have service A in my system, I have service B as well. And I would just get a, I don't know, install Kombu, and I will connect to RabbitMQ, and I'm sending messages, right? And then you realize that things are getting better and your system is growing, so you need to add more things to it. And then you start adding new methods, and you start adding new structures to your message, and you start adding new fields. And as you do that, you realize that you are basically breaking other parts of your system that were supposed to work with the older versions of your protocol and that kind of things. So it is very important to consider and to treat RPC APIs or your API between your system as if they were the user-facing APIs. And what I mean by this is that same things, the same rules you basically to all your HTTP APIs that you expect your users to consume and your client libraries to consume. You have to apply those rules, those standards to your RPC API, to the API you're using to integrate your systems. And that means you have to try to keep backward compatibility. You have to make sure it is stable. You have to make sure you return the right errors when something bad happens. And the difficult part about this is that there's no standard there, right? Yeah, you just know what RPC is, and you just know what you can do with an RPC protocol. But there's no standard saying, hey, when something goes wrong, you should return this code. Or if something happens in the other service or the other service code, you should probably do this and reply back with that, right? So you have to come up with all these ideas. You have to come up with all the API and do something with it, right? In a way that you can scale it easily and also improve it easily. So one of the first thing that I would like to highlight is that you should use versioning in your RPC API, as you do in your HTTP API most likely. And RPC APIs, since all the APIs you're using to integrate your system, since they are not user-facing, they're likely going to change more quickly because you feel free to do that, right? This is not interfering with my users. This is internal only, and I can probably play a little bit with this. And you start adding new methods, and as you add new methods, you have to bump the API version and make sure that the other nodes in your system know how to have support for that API. So having versioning is not only helpful for keeping backwards compatibility, but also helps you to do rolling upgrades, for example. So you have a whole bunch of nodes of service A running the system, but you just added a new method to your API, so you now need to upgrade them all in a way that you don't have any downtime. And since you have an API version, you can start upgrading some of the nodes that you have, test it a little bit, route some of the traffic there and make sure it works and it doesn't break anything. And the good thing about this is that the other services in your system, since they are not supporting that piece of the API and that version of the API, they won't take those messages, so they won't consume it. And they will leave those messages to be consumed by services supporting that API. So Oslo messaging, thankfully enough, we learned this on the field, and Oslo messaging has built-in support for API versions. It makes it very easy to support the different versions and have them running at the same time. But regardless of whether you're using or you will use Oslo messaging in the future or not, I would highly recommend you to have some version in your API and have a good way to recognize what versions are running in your system. Keep everything explicit, just like we like in Python. you should keep everything explicit when it comes to system integration. So Jeff Hodge, I don't know if you guys know this guy. He works for Twitter, and he said in one of his talks about integrated systems and the things they do at Twitter, that when it comes to system integration, having implicit things is the best way to fuck yourself. And that's true. That's true, because you don't have, if you have implicit things happening in your system and you have parts of the API that are not only well documented, but not explicitly detailed and thought and thoroughly thought on, and you have messages that you're sending in your system, and there's no contract in your system, basically expecting all the services in your system to know what to do with those messages traveling there. But things will happen because you won't be able to control what is going on in your system. So keep everything explicit, work on your API, work on your specifications, write them down, obviously, keep it detailed, and make sure you use versionings on top of those definitions. Propagate exceptions. We do this in OpenStack as well. I think that depending on your use case might be a useful thing to do, maybe a good idea or probably not. But you should propagate exceptions. So when service A sends a message to service B and service B does something with that message and something goes wrong, it is a good idea, I think, to propagate the exception happening in service B back to service A, assuming this is a synchronous call, back to service A, so that service A can do something with it and probably re-raise it internally and do some error handling on top of that. Instead of just parsing messages, instead of just serializing your exception in a string and sending it back to service A and it's A to parse the exception and do something with it, you can just propagate the exception and re-raise it on the other side. There are a few things about this. You don't want all the exceptions to be propagated. You just want some of them to be propagated. And the other thing is that if the services are isolated and the code is supposed to be isolated, most likely the exceptions defined in the service B are not part of your service A code. So I would probably recommend you to have a common library where all the common exceptions in your system are defined, so you can import them and propagate it correctly. And again, also messaging, thankfully enough does that for you, and it has a nice way to filter out exceptions that you don't want to propagate. Depending on your architecture, you might want to have some API level heartbeats, and this is a good way to know if the nodes you're interested to talk to are running. This, for example, is used for services. For example, in OpenStack, there's this service called Trove, which is basically database as a service. And in order to spawn up a new database instance, you need to spawn up a virtual machine first, and then install everything on that virtual machine. But you cannot install the database in that virtual machine until the virtual machine is running. So Trove would use some kind of API level heartbeats. It basically would send a message to the node and waiting for a reply back from the node. And if the node replies back, it means the node is alive, and it can probably send a request to create a database instance in that node. So depending on your use case, it might be a good idea to have some kind of API level heartbeats and use direct publishers to talk to the exact consumer that you're interested to talk to. Design by contract. I already said this like a couple of times in the talk. And again, depending on your use case, sending notifications, you probably don't care a lot about the contract, although we have had quite long discussions right now on the mailing list about whether notifications should have a contract as well. The problem about not having a contract when it comes to the messages is that the services consuming the messages, those messages will have to kind of guess what to do with the message. So they may be expecting some fields to be there, but if the fields are not there, they won't know what to do without those fields. Or there may be more fields in the message, and they won't know what to do with those extra fields there. So if you have a contract, it is definitely easier to, or more secure, more reliable to integrate your system, because you know what you're sending and you know what the other service is expecting to receive. And you know what you're going to get back from that service if you're waiting for an answer and a reply back. Keep this isolated as much as possible. You want your API to be small. You want your API to your services to be small as well. as much as possible. You want them to keep resources isolated from other services because that's why they are subsystem. Right? They are separated from other services. They're supposed to do one thing, and hopefully they will do that one thing good. And that integrating system because you want them to be distributed in other parts of your architecture. So keep those services isolated as much as possible, probably context-based. In our case, for example, all the API nodes do just API, all the compute nodes do just computing. And in the case of Nova, they also have a service dedicated to accessing the database in order to have more control on how those access to the database are done. Right? It really depends on your use case, but definitely keep that in mind. Isolate everything as much as possible, and don't share the resources in your system so that you have more control on what's happening and you can debug everything easily. Watch for dependency cycles. This might be kind of obvious, but I still wanted to say it anyway. There might be some dependency cycles in your API, since the only way, probably the only way or the most common way to figure out when there's a dependency cycle is by actually API and sending messages. And watch for those. Make sure your API is not defined in a way that it will end up in an infinite loop of messages traveling in your system, because your service A depends on service B and service B depends also on service A. Try to avoid those dependencies, unless it is not possible, obviously. But make sure there's not an infinite loop in your API. It can happen very easily, and you don't have a good view unless you are using some diagrams or something. You don't have a good view of what your API looks like until you're actually running it and you see it on the field. Transmission protocol matters. It matters if you are sending those RPC messages through HTTP or TCP or UDP. So take good care of that. Make sure you're using the protocol that works best for you, depending on your use case. Speed is not everything. When you're integrating a system, speed is not everything. Like many people say, I'm just gonna use RabbitMQ because I've heard that it's so freaking fast. It really depends on your use case. You don't have to use RabbitMQ if you don't need it. Installing RabbitMQ means that you need to maintain some service that is actually running in Erlang, and you probably don't know any Erlang, and you have to know how to maintain it. You have to learn a whole bunch of new things. You also have to learn about MQP and how to keep it running. You also have to learn how to scale it, right? So if you don't need such a low latency, I would probably recommend you to look elsewhere and try to find another service that also, another messaging service that actually works for you. Mock is not testing. So if you have your API defined and you have your unit test, using mock is actually not testing. You have to run it. Because when you're mocking, you are mocking on what you expect the API to do. But most probably you're not mocking on what the API is actually doing. Because you expect the API to do something and you write your mock on based on your assumptions. But then when you run your API in your production environment, the API does something completely different. So mocking is fine, but make sure you also have some functional tests that actually run the API as it is and integrate all the services, and you can see it. So now, to close, I'm going to go through a bit of information on what technologies are there and what you could use to integrate your services. And now I'm going to talk a little bit about brokers and other methods to do that, and what to look for when you're trying to choose the technology you want to use. Scaling brokers is hard, and I know it's documented in many different documentations, and RabbitMQ, the RabbitMQ's website has it written down, and Cupid's website has it written down, and they all claim that scaling brokers is a problem solved, and you can do that very easily. That's not true. Scaling brokers is hard, and the reason it is hard is because you have to synchronize messages. And if you care about ordering, you also have to keep order. So creating a RabbitMQ cluster is not everything. You can create a Q cluster easily, and I agree with that, and there are instructions how to do that. But that doesn't work as well as, right? So scaling brokers is really hard. It's not a solved problem at all. And that's what they are. They are brokers. They are supposed to store messages and then sending them forward. And they are the center of the whole thing. So if you don't have a cluster, some kind of replication, you basically have a single point of failure in your system, right? So you need to find a way to scale the thing out and scale it horizontally or in some way that you avoid these kind of problems. And definitely brokers, although they are good and they're freaking fast for many things, they are hard to scale. Brokers need a lot of memory, and the reason they do that is because they want to keep your messages in memory, and that's probably one of the real reasons why they are so freaking fast. And if you enable durability in RabbitMQ, if you use an exchange that is actually durable, it will store messages in your file system. But that just makes it durable. That just makes it consistent. But it doesn't mean that it is not keeping your messages in memory. So if you have a really high throughput queue, you will have a lot of messages in memory. And if you don't have enough consumers, you will fill up your memory very easily. Brokers need storage. If you're running RabbitMQ without durable equal true, you probably get into trouble very soon. Because if something happens to that node, you will lose all your messages unless you don't care at all about your messages. And if you have durable equal true, you're basically storing all messages in your file system and then amnesia database that RabbitMQ uses. And I'm mentioning here RabbitMQ, but this applies to basically any broker, but I'm assuming RabbitMQ is the most known one right now. And it will just store every message in your file system, and that will just fill your file system. If you don't consume them very quickly, consumers or workers, you will fill up your file system. So I'm not claiming that brokers are completely bad or that you shouldn't be using them, but what I'm getting at is that there are also other ways to, and other technologies that you could probably use instead of brokers. And I go back to what I was saying before. You should evaluate the technology you want to use based on your actual need. And there are other technologies like, for example, DRAMQ, which favors federation over centralization, which basically means that you have several nodes running and listening for messages in specific ports connected to bounded to specific system, and you would just send messages to the to specific nodes when you need something from them. There is something about this federation process that you need to know how your whole system is architected. So you need to have some. You also need to have some pacemaker and matchmaker in your system that you can keep control of the messages traveling and the nodes that are available or not. Which is a problem that you don't have when you are running a single broker and you know where to send the messages to. And the federation model is also applicable using NQP 1.0, which defines the protocol, the specifications for sending messages from one peer to another peer. It also standardizes how to talk to brokers, so you can have a peer that actually talks to another broker, which then sends a message to another broker. And there are many things, many fun ways to architect or deploy your federated system. And again, this just all boils down to what your needs are and whether it favors this or not. Probably having a federated system in your infrastructure, which is probably not big, is too much of a burden. But if you have a deployment that is really big and you don't want to risk on using a specific broker that is centralized, you could probably play a little bit with this and the new technologies that there are. So consider your latency boundaries. If you have requirements for a very low latency and you cannot wait for messages for more than 0.2 seconds, I would probably recommend you to pick a broker or messaging technologies that is actually fast and fits your needs. But if you don't care a lot about the latency, I would probably recommend you to use something that is easier to maintain and it doesn't use so much resources and it still fits your needs. your reliability needs. Basically means if you want your system to be fully reliable, so you want your messages not to be lost ever, you need to use some technology to store those messages for you. That means if you're using RabbitMQ, you probably want to enable durability, and you want to use exchanges with durable equal true. But if you're using a federated system, you don't have any way to store those messages because your messages are traveling directly to the nodes that are bounded to those ports, right? Because you have several nodes and they are just all listening for messages, and there's no centralized broker that is handing those messages over to the different nodes in your system. Want to use something on top of those, like, I don't know, Qp dispatch, for example, which can easily route all your messages, and you can also apply some fancy rules for storing messages and make them durable. Almost done. Consider your scale requirements. This also comes to not just the latency, but also how many queues, how many messages you are expecting to have per second, and whether you need a system that is capable of sending 1 million messages per second, or you are good with simpler. You probably are also good with implementing some kind of indoor in-house messaging bus on top of that. I don't know, HTTP, I'm making this up right now, but what I want to say is that make sure you know what your throughput is and what your scale needs are as well. And consider your security needs. This means that you also consider how, when you're deploying your architecture, when you're architecting all your API, you also have to think about, in the case of NQP 0.9 or 0.10, you also have to think about the exchanges where you want to send those messages to, and whether everyone is listening to those exchanges and the ACL for those exchanges. And you need to consider that probably a virtual host is not good for you, but you need more virtual hosts so that you can isolate the messages traveling your system, because you have a client that has some security and privacy needs that in order to fulfill them, you need to keep all the messages of that client isolated. Or you also need to encrypt those messages and before sending them and getting them back. So you need to consider all these security needs for architecting your API, and you are defining how the messages will travel in your system. And that's pretty much it. I think I used all my time, but there's still time for questions, right?
Actually, let's pick up the microphone. So, you told that in OpenStack we use horizontal integration, but I think that's not exactly true, because yes, for sure we use horizontal integration inside some service like Nova or Neutron or anything else. But if some of those services needs something that is provided by a different service, for instance, in Nova wants to create a new bare metal node, to provision a new bare metal node. It talks to a different service in OpenStack, which is called Ironic, and it does not make that go through any message bus. So it does.
Right.
But
right. In that case, it uses a vertical integration.
Yep.
Yeah, that's what I was saying before. Like the fact that you use horizontal integration or one of those methods doesn't mean that you cannot use mix them up. And actually, that's a very good observation. And another case when that happens is when you create a new instance. You create that based on an image, so Nova will just talk to Glance to get an image out of Glance and create an instance out of that image. So that basically is integration.
And every service can ask that Keystone, well, look, I need some service that provides me virtual networking, and Keystone.
Yeah, but Keystone doesn't talk to Nova, so there's no cycle in that integration at all.
All right. Yep.
So
I have a gadget for you. I don't know. Are you a gamer or a reader? I'll go for the gamer. Want a game? I don't know. I don't know what this game is.
Thank you.
No worries.
Oh.
You're welcome.
Hey, is there any question?
I have another gadget. Come on, guys. Oh, that's. You're welcome.
Hi, well, this one might be slightly off topic, but I think this is the place to ask it. I was wondering, as you were talking about this, what was your biggest challenge, be it technological or organizational, you faced in OpenStack, and how did you solve it?
Challenge in OpenStack.
Yeah.
OpenStack itself is the challenge.
Yeah, like challenge for... No, but the biggest, the most challenging task you had.
That's a setting up the development. Well, it depends on the service you're working on, right? So if you want to work on Nova, you need to set up not just Nova. You also need to set up Keystone, and you need to set up Glance and a whole bunch of other services that Nova requires to be installed in order to function. So development environments is definitely one of the hardest tasks that we strive a lot to keep as simple as possible, but we keep failing at it somehow. But it's not that we are not taking care of it. It's that it's hard because OpenStack itself is non-opinionated, or at least it tries not to be opinionated at all. So we try to keep support for different distributions, Ubuntu, Fedora, and other SUSE and other distributions that exist out there. I guess the only thing that OpenStack is actually really opinionated about is that it runs on Linux and just on Linux. But besides that, we try to make it easy for you, regardless of the distribution you're using, to work on OpenStack. But if you're using a standalone service like Glance, for example, you don't need to set up anything besides Keystone, but you can also disable that if you want. So probably the development environments is one of the hardest things. But probably the most complex one and the most interesting one, and the one that I think we are doing good but we could be better, is the CI system. And the CI system takes care of testing the whole thing. Like each patch that is proposed and is submitted to OpenStack gets run by this CI system, and then it has the integrated gate that installs all services and runs live tests all those services and make sure that there's no backward incompatible change being added to the system, and it keeps track of stable branches and master branches and all that. So it's really complex, very, very interesting, and so at least I wish I had enough time to play with it, really, but I don't. And I have a gadget for you.
Okay, thanks.
Any more questions?
Mike, you do a stereo.
Okay.
So, thank you, Flavio.
Thank you all.